What are the best nanotechnologies and nanomaterials to boost sustainability and circularity? The best nanotechnologies and nanomaterials to boost sustainability and circularity are those that enable resource efficiency, pollution reduction, renewable energy production, waste valorization, and closed-loop systems. Below is a comprehensive overview of the most impactful types: nanocellulose source, plant fibers, agricultural waste, or microbes, e.g., bacteria. Sustainability role: biodegradable, strong, lightweight alternative to plastics and composites. Enhances strength and barrier properties in packaging. Can be used in water purification membranes, coatings, and bioplastics. Circular impact: made from renewable biomass and fully recyclable or compostable. Carbon nanomaterials, graphene, carbon nanotubes, carbon dot source, biomass, captured CO2, or fossil-based carbon. Sustainability role: graphene enhances battery electrodes, supercapacitors, solar cells, and hydrogen fuel cells. Enables energy-efficient sensors, electronics, and lightweight vehicles. Circular impact: can be synthesized from waste carbon sources, e.g., methane, CO2, and integrated into long-lasting devices. Nano-enabled water purification systems. Key nanomaterials: silver nanoparticles, graphene oxide, titanium dioxide, TO2, iron oxide nanoparticles. Sustainability role: remove pathogens, heavy metals, and organic pollutants from water. Photocatalytic nanoparticles break down toxins using sunlight. Circular impact: enables reuse and recycling of water. Some nanomaterials are recoverable. Nanostructured materials for solar energy. Key examples: quantum dots, perovskite nanocrystals, nanostructured TO2, ZNO. Sustainability role: improve solar panel efficiency and reduce material use. Enable lightweight, flexible solar cells. Circular impact: potential to produce solar panels with fewer rare earths and less toxic materials. Nanomaterials and energy storage. Key nanomaterials: silicon nanoparticles, graphene, MZens, metal organic frameworks, MOFs. Sustainability role: improve energy density, lifespan, and charge rates of batteries. Enable solid-state batteries and reduce reliance on cobalt lithium. Circular impact: longer lifespans and potentially recyclable electrodes. Catalytic nanomaterials for waste conversion. Key examples: nanozeolites, palladium platinum nanoparticles, MOFs. Sustainability role: convert CO2, methane, and plastic waste into fuels or chemicals. Enable low-temperature chemical reactions using renewable energy. Circular impact: drive circular chemical manufacturing and carbon recycling. Nanocoatings for materials. Protection types: anti-corrosion, anti-fouling, self-cleaning, antimicrobial coatings. Sustainability role: extends product life, e.g., in buildings, electronics, textiles. Reduces maintenance needs and resource waste. Circular impact: promotes longer use cycles and reduces material throughput. Biodegradable and bio-based nanocomposites. Examples: starch nanocrystals, chitosan nanoparticles, lignin-based nanomaterials. Sustainability role: replace petroleum-based plastics in packaging, agriculture, and textiles. Circular impact: fully compostable or upcyclable and organic waste streams. Nano-enabled recycling and sensing. Examples: nanosensors to detect contaminants and waste streams. Magnetic nanoparticles to separate rare earths or metals. Sustainability role: improve recycling precision and material purity. Circular impact: enables recovery of high-value materials from complex waste. Smart nanomaterials for green manufacturing. Examples: self-healing polymers, stimuli-responsive nanocomposites. Sustainability role: reduce downtime and resource use in industrial processes. Enable 4D printing and adaptive, reconfigurable materials. Circular impact: extend life and reusability of products and infrastructure. Integration with circular economy strategies. Nanotechnology can prevent waste by creating more durable, efficient, and reusable materials. Design for disassembly and recyclability at the molecular level. Recover critical elements from electronic and industrial waste. Enable biological mimicry, such as materials inspired by plant cuticles or spider silk. Nanotechnologies and nanomaterials offer transformative potential for boosting sustainability and circularity across multiple sectors. By operating at the molecular and atomic scale, they allow for the precise design of materials and systems that consume fewer resources, produce less waste, and enable the continuous reuse of materials. Below is a comprehensive explanation of the most effective nanotechnologies and nanomaterials that contribute to a sustainable and circular economy. Nanocellulose, a renewable and biodegradable alternative. Nanocellulose is a nanomaterial derived from plant fibers, agricultural residues, or microbial fermentation. It is strong, lightweight, biodegradable, and produced from renewable biomass. Nanocellulose can replace petroleum-based plastics and synthetic composites in packaging, textiles, and construction materials. It also enhances the mechanical strength, barrier properties, and biodegradability of materials. Its natural origin and end-of-life compostability make it highly circular, especially when produced from waste biomass. Carbon nanomaterials, high performance in carbon capture applications. Carbon nanomaterials such as graphene, carbon nanotubes, and carbon dots possess extraordinary electrical, thermal, and mechanical properties. These materials are being used to improve the performance of batteries, supercapacitors, solar cells, and fuel cells, making renewable energy technologies more efficient and durable. Furthermore, they can be synthesized from carbon-rich waste, including carbon dioxide and methane, turning pollutants into valuable materials. Their role in energy storage and electronics also extends the lifespan of devices and reduces material input. Nano-enabled water purification systems. Nanomaterials are revolutionizing water purification by enabling highly efficient removal of contaminants such as pathogens, heavy metals, microplastics, and organic pollutants. Silver nanoparticles, graphene oxide, titanium dioxide, and iron oxide nanoparticles are commonly used for their antimicrobial, adsorptive, or photocatalytic properties. These systems enable the recycling and reuse of water in industrial, agricultural, and municipal contexts, which supports both resource conservation and circular water management. Nanostructured materials for solar energy conversion. Solar energy technologies benefit significantly from nanostructured materials. Quantum dots, perovskite nanocrystals, and nanostructured metal oxides like titanium dioxide and zinc oxide enhance the efficiency and reduce the material cost of solar panels. These nanomaterials enable lightweight, flexible, and even transparent solar cells, broadening their application in buildings, vehicles, and textiles. Using nanomaterials in solar technologies helps to expand clean energy access while reducing dependence on fossil fuels and rare materials. Nanomaterials for advanced energy storage. Nanomaterials play a crucial role in developing high-performance batteries and supercapacitors. For example, silicon nanoparticles, graphene, and MZens improve charge capacity, energy density, lifespan, and safety in lithium-ion and next-generation batteries. Metal organic frameworks, MOFs, can store hydrogen or act as conductive materials. These advances support a clean energy transition by making storage systems more sustainable and scalable. In addition, they extend battery life, reduce critical material usage, and facilitate future recycling. Catalytic nanomaterials for waste-to-value conversion. Catalytic nanomaterials such as nanozeolites, metal nanoparticles, e.g., platinum, palladium, and MOFs enable efficient conversion of waste gases, like CO2 and methane, and plastic waste into fuels, fertilizers, and industrial chemicals. These nanocatalysts operate at lower temperatures and higher selectivity, reducing energy consumption and emissions. By transforming waste into useful resources, they close the loop in material cycles and support a zero-waste, circular economy. Protective nanocoatings for long-lasting materials. Nanocoatings provide protection against corrosion, fouling, microbes, UV damage, and wear. These coatings can be self-cleaning, anti-reflective, or thermally insulating. Applying nanocoatings to buildings, electronics, vehicles, and textiles significantly extends their operational life and reduces maintenance and replacement needs. This prolongs product lifespans, reduces material throughput, and helps conserve natural resources, all of which are core goals of circularity. Biodegradable and bio-based nanocomposites. Bio-based nanocomposites, such as those made from chitosan, starch nanocrystals, or lignin nanoparticles, combine renewable biopolymers with nanoscale reinforcements. These materials can replace petroleum-based plastics in packaging, agriculture, and consumer goods. Their biodegradability ensures they can be reintegrated into the environment or composted after use. When produced from waste biomass, these nanocomposites contribute to a regenerative and circular materials economy. Nano-enabled recycling and smart sensing nanosensors can detect specific contaminants or materials in mixed waste streams, improving the accuracy and efficiency of sorting and recycling processes. Magnetic nanoparticles can be used to selectively extract valuable metals or rare earth elements from electronic waste or industrial residues. These technologies enhance resource recovery and enable the reintegration of critical materials into the supply chain, supporting closed-loop manufacturing systems. Smart nanomaterials for sustainable manufacturing. Smart nanomaterials, including self-healing polymers and stimuli-responsive nanocomposites, reduce material losses and manufacturing and extend product usability. These materials can repair themselves after damage or adapt to environmental conditions, reducing the need for replacements. This leads to decreased consumption of raw materials and energy while encouraging modular, repairable, and upcyclable product designs. Nanotechnology provides powerful tools to redesign materials, energy systems, and waste flows for a more sustainable and circular world. By enhancing material efficiency, enabling clean energy, reducing pollution, and facilitating recycling and biodegradation, nanotechnologies help close resource loops and decouple economic development from environmental degradation. Their integration across industries, from agriculture and water to energy and construction, can accelerate the global shift to circular and regenerative systems. There are many real-world examples and prototypes of nanotechnologies and nanomaterials that are already demonstrating their potential to boost sustainability and circularity. Below is a detailed list of technologies, research projects, commercial products, and functional prototypes aligned with each category discussed earlier. Nanocellulose examples: Stora Enso and UPM developed nanocellulose films and packaging materials as biodegradable alternatives to plastics. EMPA, Swiss Federal Lab, created nanocellulose food packaging with antimicrobial properties that extends shelf life. Celluforce, Canada, produces cellulose nanocrystals, CNCs, for applications in packaging, composites, paints, and adhesives. Prototypes: biodegradable electronics, nanocellulose-based transistors and circuit boards developed at Linköping University, Sweden. Water filters, nanocellulose membranes for pathogen removal, in pilot testing for decentralized water treatment. Carbon nanomaterials examples: Skeleton Technologies, Estonia, uses curved graphene in commercial supercapacitors for electric buses and energy grids. Direct air capture plus graphene, labs have demonstrated turning captured CO2 into graphene, e.g., Rice University's flash graphene process. Prototypes: flexible solar panels, graphene layers used in ultra-thin, transparent photovoltaics, e.g., MIT and University of Manchester. Graphene-enhanced asphalt, used in road surfacing in the UK and Italy to increase durability and reduce maintenance. Nano-enabled water purification examples: Puralytics solar bag, uses nanoparticles and sunlight to purify water without chemicals or power. Oximum MABR, incorporates nanostructured membranes to clean wastewater more efficiently using biofilms. Prototypes: graphene oxide membranes, developed by the University of Manchester for salt and heavy metal removal. Iron oxide nanocomposites, used for arsenic removal in groundwater in India and Bangladesh. Nanostructured solar materials examples: Oxford PV, commercializing perovskite solar cells enhanced with nanomaterials for up to 29% efficiency. Solarinics, manufactures dye-sensitized solar cells, DSSCs, using nano-TO2 as the photoactive material. Prototypes: transparent solar windows, produced with quantum dots or perovskite nanolayers, e.g., by Ubiquity and Next Energy. Nanostructured coatings, used to trap more light and improve absorption in solar panels. Fraunhofer ISE Research, nano-enhanced energy storage examples: Sila Nanotechnologies, commercializes silicon nanoparticle anodes to increase lithium-ion battery capacity by up to 20%. Tesla's 4680 batteries, include nanoscale material engineering for higher energy density, prototypes, solid-state batteries. Companies like QuantumScape and Toyota use nanomaterials and electrolyte layers for higher safety and performance. MOF-based hydrogen tanks, prototypes that store hydrogen at lower pressures using metal organic frameworks. Catalytic nanomaterials for waste conversion examples. LanzaTech uses nanoparticle catalysts to convert industrial CO2 and company into ethanol and chemicals. Electrochia employs nanocatalysts and reactors to transform CO2 and hydrogen into methane, power to gas. Prototypes, photocatalytic CO2 fuel systems, developed by EDH Zurich and others using TO2 and copper nanocatalysts to produce methanol. Plasmonic nanoparticles, used to convert plastic waste to hydrogen gas with sunlight. University of Cambridge research. Nanocoatings for protection and efficiency examples, Latuzan paint. Stow AG, mimics lotus leaves using nanostructured surfaces for self-cleaning walls. Nanoseptic, produces antimicrobial surfaces for door handles and touch screens using mineral nanocrystals. Prototypes, energy-saving window coatings, nanostructured films that reduce UV and IR penetration, now in building integrated applications. Smart textiles, clothing with nano-silver or nano-TO2 coatings that self-clean or respond to temperature. Bio-based nanocomposites examples, NatureWorks, produces PLA bioplastics enhanced with nanoclay for better barrier properties in food packaging. PolyOne, developed nanoclay reinforced biodegradable bags and films for agriculture and retail. Prototypes, 3D printed bioplastics, combining nanocellulose or chitosan with PLA to create compostable parts and packaging. Green electronics, biodegradable sensors and circuits using starch and lignin nanoparticles under EU-funded projects like GreenAT. Nano-enabled recycling and smart sensing examples, AMP Robotics, integrates AI and nanosensors in robotic recycling arms for precise material sorting. NanoScent, Israel, uses nanotechnology to smell chemicals in waste streams to separate materials. Prototypes, magnetic nanomaterials, used to recover rare earths from e-waste by companies like urban mining company Smart Waste Bins, equipped with nanosensors to detect contamination and sort recyclables automatically, used in smart cities. Smart nanomaterials and green manufacturing examples, BASF, developed self-healing polymers using micro and nano-encapsulation for automotive and aerospace coatings. Henkel produces nanostructured adhesives that allow for low-energy assembly in electronics. Prototypes, 4D printed nanomaterials, shape-shifting structures that respond to moisture or temperature, useful in robotics and green design. Thermal management films, nano-enhanced materials in production lines to reduce energy losses in equipment. Nanocellulose, a renewable material for green manufacturing. Nanocellulose is derived from plant fibers, agricultural residues, or bacteria. It is extremely strong, lightweight, and biodegradable. One example is Celluforce, a Canadian company that manufactures cellulose nanocrystals, CNCs, for use in sustainable packaging, paints, and adhesives. Stora Enso and UPM, two Finnish companies, are producing nanocellulose films and coatings as alternatives to fossil fuel-based plastics. Researchers at EMPA, Swiss Federal Laboratories, developed antimicrobial nanocellulose food packaging, which prevents spoilage and extends shelf life. Nanocellulose is also being used in prototype biodegradable electronics, such as transistors and sensors made at Linköping University in Sweden. Because it is produced from renewable biomass and is compostable at the end of life, it supports circular material cycles and reduces plastic waste. Carbon nanomaterials, enhancing energy, durability, and carbon reuse. Carbon nanomaterials such as graphene, carbon nanotubes, and carbon dots are known for their exceptional strength, electrical conductivity, and thermal properties. Skeleton Technologies, based in Estonia, uses curved graphene in high-performance supercapacitors that are already powering electric buses and energy storage systems. Rice University developed a process called flash graphene, which converts waste materials and carbon emissions directly into graphene in seconds, offering a circular route to valuable materials. Graphene-enhanced asphalt, currently used in roads in Italy and the UK, provides longer durability, which reduces maintenance and resource use. Graphene also plays a critical role in flexible solar panels and advanced electronics, contributing to lightweight, long-lasting, and energy-efficient systems. Nano-enabled water purification systems. Clean and reusable water nanotechnology enables advanced water purification through nanomaterials like silver nanoparticles, graphene oxide, and iron oxide nanocomposites. These materials eliminate bacteria, viruses, heavy metals, and chemicals from contaminated water sources. The Puralytics solar bag uses nanoparticles activated by sunlight to purify drinking water without the need for electricity or chemicals, making it ideal for remote or disaster-affected areas. Graphene oxide membranes, developed by the University of Manchester, can desalinate seawater and remove toxic pollutants. In India and Bangladesh, iron oxide nanoparticles are being tested to remove arsenic from groundwater. These nano-based systems allow for the safe reuse and recycling of water, reducing environmental contamination and promoting circular water use. Nanostructured materials for solar energy. Clean and efficient power nanostructured materials significantly improve the efficiency and versatility of solar energy systems. Oxford PV has developed perovskite solar cells, which are enhanced with nanomaterials to achieve over 29% conversion efficiency, much higher than traditional silicon panels. These cells are also lightweight and suitable for flexible applications. Companies like Ubiquity and Next Energy Technologies are creating transparent solar windows using quantum dots and perovskite nanolayers. These allow buildings to generate electricity through their windows. Solarnix manufactures dye-sensitized solar cells that use nano-TO2 for better light absorption. Nanotechnology also enables light-trapping coatings, which reduce material usage and increase energy generation in solar panels, supporting sustainable and decentralized energy systems. Nano-enhanced energy storage. Better batteries for a green future. Nanomaterials are improving energy storage by enhancing the performance of batteries and supercapacitors. Nanotechnologies has developed silicon nanoparticle anodes that increase lithium-ion battery capacity by up to 20%, extending the range of electric vehicles while reducing the amount of lithium and cobalt needed. Tesla's 4,680 batteries incorporate nanoscale engineering to improve energy density and lifespan. Companies like QuantumScape and Toyota are developing solid-state batteries using nanostructured electrolytes, which offer faster charging, longer lifespan, and improved safety. Additionally, metal organic frameworks, MOFs, are being prototyped for hydrogen storage, enabling the clean and efficient use of hydrogen as a renewable fuel. These technologies promote circularity by reducing raw material needs and enabling easier battery recycling. Catalytic nanomaterials for converting waste to fuel and chemicals. Catalytic nanomaterials can transform industrial waste, carbon dioxide, and methane into useful fuels and chemicals. LanzaTech uses engineered microbes and nanoparticle catalysts to convert carbon-rich emissions into ethanol and other chemicals at commercial scale. Electrochia, based in Germany, uses a similar system to convert CO2 and hydrogen into methane, a renewable gas, using nanocatalysis. Researchers at ETH Zurich have developed photocatalytic nanoreactors that turn CO2 into methanol using sunlight and titanium dioxide nanoparticles. The University of Cambridge created a prototype that uses plasmonic nanoparticles to convert plastic waste into hydrogen gas using sunlight. These systems close the loop by turning pollution and waste into energy and industrial feedstocks. Nanocoatings for durability and resource efficiency. Nanocoatings protect materials and products from environmental damage, extending their lifespan and reducing the need for maintenance. Stow AG developed Latusan paint, which mimics the self-cleaning properties of lotus leaves using nanostructures. This reduces the need for water and cleaning chemicals on buildings. Nanoseptic produces self-cleaning antimicrobial surfaces for public touch points like door handles and elevators using mineral nanocrystals. These coatings help reduce disease transmission and cleaning frequency. Nanocoatings are also used in smart windows to control light and heat, improving energy efficiency in buildings. By reducing wear and extending product life, nanocoatings reduce material consumption and support circularity. Biodegradable and bio-based nanocomposites. Bio-based nanocomposites use natural polymers like starch, lignin, or chitosan combined with nanoscale reinforcements to create materials that are strong, compostable, and environmentally friendly. NatureWorks develops PLA bioplastics reinforced with nanoclays for packaging that resist moisture and oxygen. Poly-1 created biodegradable bags and films enhanced with nanomaterials for agriculture and consumer goods. These materials break down naturally and can be composted, reducing plastic pollution. In the EU-funded ReNet project, researchers have built biodegradable electronics using starch and lignin nanoparticles, showing the potential for compostable tech products. Nano-enabled recycling and smart waste management. Nanotechnology is being used to improve recycling systems through advanced detection and separation methods. AMP Robotics employs AI-powered robotic arms equipped with nanosensors to identify and sort materials in recycling centers. This increases the purity and efficiency of recovered resources. NanoScent, an Israeli startup, uses nanoscale chemical sensors to smell and identify substances in waste streams, improving the sorting of recyclable plastics and organic waste. Urban Mining Company uses magnetic nanoparticles to extract rare earth elements from e-waste. These technologies increase the recovery of valuable materials and reduce landfill waste, making resource use more circular. Smart nanomaterials in green manufacturing. Smart nanomaterials adapt to environmental changes and can repair themselves, reducing waste and increasing efficiency. BASF has developed self-healing coatings using nano-encapsulated agents that activate when the coating is scratched, extending product lifespans in the automotive and aerospace industries. Henkel uses nanostructured adhesives that bond materials at low temperatures, lowering energy consumption during manufacturing. Researchers are also developing 4D printed nanomaterials that change shape in response to stimuli like moisture or heat, enabling adaptable and reconfigurable products. These materials reduce waste and facilitate modular and repairable product design. Across energy, water, materials, manufacturing, and recycling, nanotechnologies are being developed and deployed to enable sustainable and circular systems. These innovations reduce environmental impact, extend product lifespans, recover valuable resources, and enable low waste, low carbon production. Many of these technologies are already in use or undergoing commercialization, showing that nanotechnology is not just theoretical, but an essential part of the future of sustainability. How can we generate clean energy, stop climate change, and clean up pollution and waste with nanotechnologies and nanomaterials? We can generate clean energy, stop climate change, and clean up pollution and waste using nanotechnologies and nanomaterials by leveraging their unique properties at the atomic and molecular scale to enhance energy systems, capture and convert emissions, and enable circular resource cycles. Below is a comprehensive, complete sentence explanation of how nanotechnology enables these outcomes. Generating clean and renewable energy. Nanomaterials improve solar, wind, hydrogen, and battery technologies. Nanostructured solar materials, such as perovskites and quantum dots, enable next-generation solar cells that are more efficient, lighter, cheaper, and even transparent. These nanomaterials allow for solar panels integrated into windows, fabrics, or portable devices, significantly expanding clean energy access. Nanocatalysts are used in hydrogen production systems, especially in water electrolysis, by lowering the energy required to split water molecules. Nanoparticles of platinum, molybdenum sulfide, or cobalt enhance these reactions and make green hydrogen more cost-effective. Nano-enhanced wind turbine blades, made with carbon nanotubes or graphene-reinforced composites, are lighter and stronger, enabling longer blades and increased energy capture. Nanomaterials in batteries, such as silicon nanoparticle anodes or solid-state electrolytes, significantly improve the capacity, lifespan, and safety of lithium-ion and next-generation batteries. This helps scale renewable energy storage for homes, vehicles, and grids. These technologies support the shift to 100% clean, decentralized, and renewable energy systems, essential for climate mitigation. Stopping climate change by capturing and reusing CO2 and methane. Nanotechnology allows efficient carbon capture, conversion, and recycling. Metal organic frameworks, MOFs, and carbon nanomaterials, like graphene or carbon nanotubes, are being used to capture CO2 from air or industrial exhaust with high efficiency due to their massive surface area and selective binding properties. Once captured, nanocatalysts can convert CO2 into useful fuels and chemicals, such as methanol, ethanol, methane, or even plastics. For example, copper nanoparticle catalysts can reduce CO2 to hydrocarbons using sunlight and water, mimicking artificial photosynthesis. Plasmonic nanostructures, e.g., gold or silver nanoparticles, can concentrate light energy to drive photocatalytic CO2 reduction, enabling solar-driven fuel production directly from carbon emissions. Nanomaterials also enhance methane sensors and catalysts that detect and destroy leaks in landfills, pipelines, and farms, preventing the release of this potent greenhouse gas. These processes close the loop by transforming greenhouse gases into circular resources instead of pollution. Cleaning up pollution and environmental waste. Nanomaterials can break down, filter, or remove pollutants at the molecular level. Graphene oxide membranes, carbon nanotube filters, and nanocellulose-based membranes are used to remove heavy metals, microplastics, pathogens, and organic toxins from polluted water sources. These are far more efficient and compact than traditional filters. Nanophytic catalysts such as titanium dioxide nanoparticles can break down pesticides, dyes, pharmaceuticals, and oil residues in air, soil, and water using only sunlight. These catalysts accelerate oxidation reactions that neutralize pollutants. Magnetic nanoparticles can be used to extract pollutants such as arsenic, lead, mercury, and even microplastics from water. After binding with contaminants, they can be removed with a magnet and reused. Nanosponges and aerogels, made from silica or carbon, soak up oil spills, organic solvents, and toxic gases. They are reusable, biodegradable, and highly effective in emergencies. These technologies allow us to detoxify ecosystems, restore clean water and soil, and prevent human and wildlife exposure to harmful waste. Reducing industrial emissions and waste through nanotechnology enables low-waste, energy-efficient manufacturing. Self-healing nanomaterials reduce waste and extend product lifespan by repairing themselves, minimizing the need for replacements or repairs. Nano-enhanced catalysts are used in green chemical processes that reduce the need for high temperatures, toxic solvents, or excess energy, leading to cleaner production. Nanocoatings protect metals and surfaces from corrosion, UV damage, and biofouling, reducing the environmental impact of maintenance, painting, and replacement. Smart nanomaterials enable 4D printing, modular design, and lightweight structures that use less material and energy during production and transport. These improvements support a circular, low-carbon economy by eliminating industrial inefficiencies and unnecessary waste. Enabling circular economy and resource recovery. Nanotech supports recycling, regeneration, and upcycling of materials. Nanosensors embedded in smart packaging and waste bins detect contamination, track material types, and improve automated recycling systems, as seen in AMP robotics. Magnetic nanomaterials can recover precious metals, rare earth elements, and electronic components from e-waste with high precision, reducing the need for mining. Biodegradable nanocomposites made from chitosan, lignin, or nanocellulose are replacing single-use plastics and can be composted or regenerated at end of life. Nanotechnologies also enable regenerative agriculture by delivering nutrients or microbes precisely using nanocarriers, improving soil health and productivity while reducing runoff and waste. These systems extend the life of resources, eliminate pollution, and support zero-waste societies. Nanotechnology as a climate and sustainability accelerator. Nanotechnologies can replace harmful materials, capture and convert greenhouse gases, generate clean power, and remediate pollution with minimal energy and high efficiency. When integrated into industry, energy, water, and agriculture, they help prevent emissions and stop climate change, recover and reuse carbon, materials, and waste, power economies with clean, renewable energy, detoxify polluted environments and ecosystems, build long-lasting, regenerative products and infrastructure. Together, these innovations offer a powerful toolkit to build a cleaner, safer, and more circular world, addressing climate and pollution at their roots. Restoring water, soil, and air. Photocatalytic minerals such as titanium dioxide, zinc oxide, and doped graphitic carbon nitride use light to generate reactive oxygen species that oxidize and break down organic pollutants, and they can be applied as immobilized coatings or mats to degrade pesticides, dyes, volatile organic compounds, and many microbial contaminants. Because unmodified TiO2 is mainly UV active, Researchers and manufacturers commonly dope its lattice or combine it with visible light-absorbing nanomaterials so that it will operate under sunlight, and this makes rooftop, facade, and canal liner applications feasible at scale. Advanced adsorption materials like metal organic frameworks, covalent organic frameworks, functionalized activated carbons, and iron oxide nanoparticles bind very low concentrations of heavy metals, phosphate, ammonium, PFAS, and other trace contaminants by providing extremely high surface area and tunable binding sites, and these sorbents are most effective when they are designed for regeneration by pH, thermal, or electrochemical swings so that captured contaminants can be recovered or immobilized safely. Magnetic nanocomposites combine sorbent chemistry with an iron core that allows rapid, low-energy separation of loaded materials by magnets, and they are particularly valuable for small-scale groundwater, industrial effluents, and e-waste leachates where rapid recovery and reuse of the sorbent are required. Nano-zero-valent iron and other bio-nano remediation approaches provide targeted reducing conditions and can stimulate in situ biodegradation of legacy chlorinated solvents and hydrocarbons. And these approaches are already in commercial use at many contaminated sites when proper plume containment and monitoring plans are implemented. Supercharging clean energy and storage. Nanostructured photovoltaic technologies such as perovskite and quantum dot solar cells increase solar conversion efficiency and permit lightweight, flexible, and semi-transparent modules that can be integrated into building facades, greenhouse glazing, and vehicle surfaces. Manufacturers typically pair these nanostructures with barrier layers and encapsulants to manage stability and prevent toxic elements from leaching at end of life. Nano-engineered electrocatalysts, including layered transition metal dichalcogenides, doped nickel iron oxides, and copper-based nanocatalysts, lower the overpotentials for the hydrogen evolution and oxygen evolution reactions, and can also catalyze electrochemical CO2 reduction to chemicals such as formate, methanol, ethylene, and other feedstocks, which enables on-site synthetic fuel and chemical production powered by renewable electricity. Battery performance and lifetime are improved by nanoscale electrode engineering, for example by using silicon nanoparticles in composite anodes, conductive 2D materials, MZNs, as current collectors, and ceramic or polymer nanolayers as solid electrolytes. These nanoscale improvements raise energy density, speed charging, and increase cycle life, and they also make it easier to deploy second-life batteries for grid smoothing and community storage. Designing circular materials and products. Nanocellulose in the form of cellulose nanocrystals and cellulose nanofibrils provides a renewable, high-strength nanofiller for bioplastics, coatings, and construction panels. And because it is produced from biomass residues, it helps close carbon and material loops when products are designed for composting or chemical recycling. Graphene and carbon nanotube additives enable lightweighting, improve conductivity, and enhance mechanical durability in composites and infrastructure materials, which reduces material throughput over a product's lifetime. Sourcing these carbon nanomaterials from waste-derived or CO2-derived routes further increases circularity. Self-healing and stimuli-responsive nanopolymers restore function after damage by releasing encapsulated repair agents, or by reversible chemistry at the nanoscale, and by extending useful lifetime. These materials reduce production demand and waste. Ultra-thin nanobarrier coatings and selective permeation layers allow the creation of monomaterial packages with the same barrier performance as multi-layer laminates. And this design for recyclability simplifies downstream reprocessing and improves the purity of recycled streams. Turning waste into feedstock. Nanocatalytic upcycling uses size and shape controlled metal and metal oxide nanoparticles, supported catalysts, and plasmonic nanostructures to convert greenhouse gases and polymer waste into higher value feedstocks under much milder temperatures and with higher selectivity than traditional catalysts. For example, copper and silver-based nanocatalysts can reduce CO2 electrochemically into multi-carbon products, and plasmonic nanoparticles can concentrate sunlight to drive selective bond scission in polyethylene or polypropylene, so these plastics are converted into oils and monomers that can be refined back into polymers. Precision sorting and recovery is enabled by nanosensors, SURS, surface-enhanced Raman scattering tags, and magnetic labeling. And these nanoscale detection and separation technologies dramatically increase the purity and economic value of secondary materials such as rare earth magnets, battery metals, and high-quality polymer feedstocks, regenerating ecosystems in agriculture. Nano-enhanced fertilizers and micronutrient chelates provide slow, targeted nutrient release and enhance root uptake efficiency, which reduces nutrient runoff, eutrophication, and fertilizer waste while improving yields on degraded soils. Biodegradable nanocarriers that deliver beneficial microbes or soil amendments can accelerate microbial restoration and carbon sequestration in soils. And these carriers are designed to degrade after they have released their payload so that no persistent nanoparticle load remains in the environment. Non-biocidal anti-fouling nanotextures rely on engineered surface topography rather than toxic agents to prevent biofilm formation. And these physical approaches reduce the environmental hazards associated with anti-fouling paints while delivering energy savings for shipping and aquaculture. Spectral selective nanofilms and radiative cooling coatings are able to selectively pass photosynthetically active radiation to crops while rejecting infrared or UV, or to passively radiate heat to the cold sky. And these films therefore reduce irrigation and HVAC loads and enable more productive, lower carbon greenhouses and buildings. Cross-cutting enablers, sensors and membranes. Two-dimensional materials such as MZNs and graphene derivatives enable extremely sensitive, low-power sensors that detect trace gases, nutrients, and pollutants in real time. And when these sensors are networked with edge analytics, they support rapid leak detection, precision irrigation, and targeted remediation actions. Low-pressure, high-selectivity membranes constructed from graphene oxide, carbon nanotube arrays, or laminated nanocellulose promise desalination, micropollutant removal, and energy-efficient industrial water reuse at much lower energy cost than conventional reverse osmosis. When membranes are deployed in immobilized, laminated forms with regeneration and take-back schemes, these enablers strengthen measurement, reporting, and verification capabilities which are essential for performance contracts, green finance, and credible environmental claims. Fast, high-impact deployment bundles. Deploying a few complementary nanotechnologies together yields rapid planetary returns. For cities, coating canal liners with photocatalytic minerals, installing phosphate capture geotextiles at outfalls, and adding low-pressure reuse membranes to treatment plants rapidly raises urban water circularity. For buildings, retrofitting windows with transparent photovoltaic films, adding radiative cooling roof paints, and applying spectral selective nanofilms to greenhouses cuts operational emissions while providing on-site electricity. For infrastructure, incorporating graphene-modified asphalt and corrosion-resistant nano-coatings into roads and bridges lengthens service life and cuts embodied carbon associated with repair and replacement. For industry, collocating nano-catalyst electrolyzers with CO2 sources and coupling them to nanosensor MRV networks turns point emissions into marketable fuels and chemicals while providing reliable monitoring. For agriculture, combining slow-release nano-fertilizers, biodegradable probiotic carriers, and spectral greenhouse films reduces runoff, raises yields, and increases soil carbon sequestration. Safety, governance, and design for circularity. Nanotechnologies should be deployed with the explicit goals of immobilizing particles where possible, designing end-of-life take-back and regeneration pathways, and avoiding persistent biocidal nanomaterials unless their benefits clearly outweigh ecological risks. Life cycle assessment, fate and transport modeling, and standardized toxicology testing, for example following internationally recognized nanotesting guidelines, must be performed before large deployments, and procurement contracts should require environmental product declarations, material passports, and recycling commitments. Worker exposure controls, powder handling best practices, and validated monitoring of release into air, water, and soils are essential during manufacture, installation, and maintenance. Finally, preference should be given to biodegradable carriers, encapsulated catalysts, and recoverable sorbents so that valuable material flows are closed instead of lost. When nanotechnologies are chosen and engineered for immobilization, regeneration, and end-of-life recovery, they offer high-leverage levers to clean water and air, decarbonize energy, convert waste into feedstocks, and extend the useful life of infrastructure and products. By pairing photocatalytic remediation, selective nanoadsorbents, advanced membranes, nanocatalytic upcycling, bio-based nanocomposites, and nano-enhanced energy systems with rigorous safety testing and closed-loop recovery strategies. It is possible to regenerate ecosystems, greatly reduce pollution, and accelerate the transition to a circular, low-carbon economy. Nanotechnology for planetary regeneration in a fully sustainable future. Nanotechnology, which involves engineering and manipulating materials at the scale of atoms and molecules, has emerged as one of the most transformative tools for solving humanity's greatest environmental challenges. The unique properties of nanomaterials, such as their massive surface area to volume ratio, tunable chemical reactivity, electrical conductivity, and light absorption, make them capable of performing tasks that conventional materials cannot achieve. By designing materials with precision at the nanoscale, we can capture greenhouse gases, clean polluted ecosystems, generate limitless renewable energy, and create a circular economy that eliminates waste. This essay explores the most impactful nanotechnologies that can regenerate ecosystems and accelerate global sustainability in energy, water, food, industry, and urban systems. Nanotechnologies for clean and infinite energy. Achieving sustainability begins with replacing fossil fuels and creating a fully renewable energy system. Nanotechnology is revolutionizing energy production, storage, and efficiency. Nanostructured solar materials such as perovskites, quantum dots, and organic photovoltaics have transformed solar energy into one of the most promising solutions. Unlike traditional silicon solar panels, these materials can be engineered to absorb a broader spectrum of sunlight, achieve efficiencies above 30%, and be printed onto lightweight, flexible films. This allows solar power to be integrated into windows, building surfaces, clothing, and vehicles, bringing decentralized clean energy everywhere. In addition, nanocatalysts accelerate the production of green hydrogen by making water electrolysis cheaper and more efficient. Nanoparticles of platinum, nickel, and molybdenum sulfide dramatically lower the energy required to split water into hydrogen and oxygen, making hydrogen a viable fuel for industries and transportation. For energy storage, nano-engineered batteries with silicon anodes, solid-state electrolytes, and graphene electrodes offer much higher capacity, faster charging, and longer lifespans than current lithium-ion batteries. Combined with nano-enhanced supercapacitors, these systems can stabilize renewable energy grids, support electric transportation, and eliminate dependence on fossil fuels. Nanotechnology is also being applied to wind and tidal power systems through carbon nanotube composites that create lighter, stronger turbine blades and improve energy capture. Together, these breakthroughs promise a future where clean, decentralized energy is abundant, affordable, and accessible. Atmospheric carbon capture and climate restoration. Reversing climate change requires removing billions of tons of carbon dioxide and methane from the atmosphere. Nanomaterials excel at this because they offer unparalleled surface area and selectivity for gas capture. Metal organic frameworks, for example, are crystalline nanomaterials with tunable pore structures that can absorb CO2 with extraordinary efficiency. They are already being integrated into direct air capture systems to extract carbon from the atmosphere. Similarly, graphene oxide sponges and aerogels can trap methane and other greenhouse gases. Once captured, nanocatalysts can transform carbon emissions into useful fuels and chemicals. For instance, copper nanoparticle catalysts powered by sunlight can convert CO2 into hydrocarbons, effectively turning pollution into renewable energy. Other research is exploring artificial photosynthesis systems that mimic natural plant processes, using nanostructured semiconductors to convert sunlight, water, and CO2 into sugars or fuels. By combining nanotechnology-based capture, storage, and conversion, we can not only halt emissions but also actively regenerate atmospheric balance and reverse climate damage. Nanotechnology for water purification and ecosystem recovery. Clean water is essential for life, yet pollution from heavy metals, microplastics, agricultural runoff, and industrial waste threatens ecosystems worldwide. Nanotechnology offers powerful solutions for restoring water quality and preventing scarcity. Graphene oxide membranes can filter water at the molecular level, removing salts, toxins, and pathogens more efficiently than traditional reverse osmosis systems. These membranes are thin, durable, and require far less energy, making large-scale desalination and purification feasible even in drought-prone regions. Magnetic nanoparticles offer a revolutionary way to clean contaminated water. These particles can be coated with functional groups that bind to specific pollutants, such as arsenic, lead, or oil. Once attached, they can be retrieved with magnets, enabling rapid and cost-effective cleanup. Nanophytic catalysts like titanium dioxide nanoparticles can harness sunlight to break down pesticides, pharmaceuticals, and organic waste in water and soil. These catalysts create hydroxyl radicals that degrade toxins into harmless compounds, effectively detoxifying ecosystems without harmful chemicals. These innovations, combined with nanobiosensors that detect pollutants in real time, provide a comprehensive toolkit for regenerating rivers, lakes, and oceans. Zero-waste industry and a circular economy. Nanotechnology enables a paradigm shift from a linear, wasteful industrial model to a circular economy where resources are continually reused. For example, nanostructured catalysts are revolutionizing chemical manufacturing by making processes faster, cleaner, and more energy efficient. Many industries traditionally require high temperatures, toxic solvents, and massive energy input. Nanocatalysts reduce these demands, lowering emissions and resource consumption. Smart nanomaterials such as self-healing coatings, anti-corrosion nanolayers, and lightweight composites extend the lifespan of infrastructure, vehicles, and electronics, reducing replacement cycles and waste. Recycling is also being enhanced by nanotechnology. Magnetic nanomaterials can extract valuable metals and rare earth elements from e-waste, while nanosensors embedded in packaging and products can enable automated sorting and material recovery. This ensures that materials such as plastics, metals, and electronics remain in circulation instead of ending up in landfills or oceans. Nanotechnology also offers biodegradable nanocomposites derived from cellulose, chitosan, and starch that can replace single-use plastics, creating a regenerative materials economy. Nanotechnology for agriculture and soil restoration. Agriculture can shift from being a major source of emissions to a regenerative system with nanotechnology. Nanofertilizers and nanopesticides release nutrients and protective agents precisely when and where they are needed, minimizing waste and reducing harmful runoff into waterways. This improves soil health and prevents ecosystem damage. Nanobiosensors can monitor soil nutrient levels, moisture content, and microbial activity in real time, guiding regenerative farming practices. Nanoclays and biochar nanoparticles help restore degraded soils by retaining moisture and nutrients, improving carbon sequestration. Additionally, nano-enabled vertical farming and hydroponics allow crops to be grown with minimal water and no soil, reducing pressure on forest and arable land while ensuring food security. These systems can be powered by nano-enhanced LED lighting and solar films, making agriculture more sustainable and productive. Pollution cleanup and environmental detoxification. Beyond prevention, nanotechnology provides the ability to actively remove existing pollution. Nanosponges made from carbon, silica, or cellulose aerosols can absorb oil spills, solvents, and persistent organic pollutants. These sponges are reusable and highly efficient, making them ideal for large-scale cleanups. Nanoiron particles can break down chlorinated compounds and other toxic pollutants in groundwater through chemical reduction, offering a powerful tool for contaminated site remediation. Moreover, photocatalytic nanocoatings on buildings and roads can help clean urban air by breaking down nitrogen oxides, sulfur oxides, and volatile organic compounds using sunlight. In effect, cities can become giant air purifiers. Nanotechnology and nature-inspired design. Nanotechnology not only solves environmental problems but also draws inspiration from nature to create sustainable materials. Lotus leaf-inspired self-cleaning nanocoatings reduce the need for harmful cleaning agents, while spider silk-inspired biodegradable nanofibers offer a lightweight, strong alternative to plastics. Mimicking biological systems at the nanoscale can lead to new circular and regenerative designs, closing material loops and reducing ecological impact. A nanotechnology-driven planetary renaissance. Nanotechnology has the potential to drive a planetary-scale transformation by regenerating ecosystems, reversing pollution, and decarbonizing every sector of society. Its applications range from atmospheric carbon capture and solar fuel production to water purification, zero-waste manufacturing, precision agriculture, and large-scale pollution cleanup. By harnessing the atomic-scale precision of nanoscience, humanity can design a sustainable civilization that harmonizes with natural systems instead of depleting them. The integration of nanotechnology with renewable energy, biotechnology, artificial intelligence, and circular economy principles will lead to a world where waste is eliminated, resources are endlessly reused, and the environment thrives. If adopted at scale, these technologies can transform Earth into a regenerative, biodiverse, and self-sustaining planet, ensuring a future where human progress supports ecological health rather than threatening it. What are the best nanotechnologies to turn pollution and waste into production? Nanotechnology offers some of the most advanced tools to turn pollution and waste into valuable resources. By manipulating materials at the nanoscale, we can break down harmful substances, extract raw materials, and even convert waste into energy, chemicals, fuels, and new materials. Below is a comprehensive explanation of the best nanotechnologies designed to close the loop on waste and transform pollution into productive outputs. Nanotechnologies that transform pollution and waste into resources. Nanocatalysts for waste to fuel conversion. How it works. Nanocatalysts, tiny catalysts engineered at the atomic scale, dramatically speed up chemical reactions, making it possible to transform pollutants and waste into clean fuels. Carbon dioxide to fuels. Copper, nickel, or cobalt. Nanocatalysts can convert CO2 into methanol, ethanol, or synthetic hydrocarbons using renewable energy. This technology enables carbon capture and utilization, turning a greenhouse gas into a resource. Plastic waste to fuel. Nanocatalysts like zeolites and titanium nanoparticles can break down plastic waste into high-value fuels or feedstocks for the chemical industry through advanced pyrolysis. Methane utilization. Palladium and platinum nanocatalysts enable low-energy conversion of methane emissions from agriculture and landfills into methanol or hydrogen. Impact. Turns harmful greenhouse gases and solid waste into energy, reducing emissions while creating valuable products. Nano-enhanced recycling of electronic and industrial waste. How it works. E-waste is rich in rare earth elements, gold, silver, and copper, but extracting them is difficult. Nanotechnology offers precise separation and recovery tools. Magnetic nanoparticles, coated with specific ligands, they can selectively bind to rare earth metals or precious metals in waste streams and pull them out with a magnet. Nanofiltration membranes, ultra-thin membranes can separate and recover high-purity metals and minerals from industrial wastewater, mine tailings, and electronic waste leachates. Nanostructured absorbents, materials like metal organic frameworks or graphene oxide sponges, can selectively capture valuable metals like lithium or cobalt from batteries, making closed-loop battery recycling efficient. Impact. Minimizes mining, reduces toxic waste, and creates a circular economy for electronics and batteries. Nanophotocalysis for waste decomposition and chemical recovery. How it works. Photocatalysts like titanium dioxide nanoparticles use sunlight to break down complex organic pollutants, pesticides, dyes, oil residues into basic molecules. These reactions can convert hazardous industrial chemicals into feedstock for new production cycles. Doped CO2 nanoparticles can even capture nitrogen from wastewater to produce ammonia, a valuable fertilizer. This process also works for air purification, where harmful NOx, SOx, and VOCs are broken down into harmless or useful compounds. Impact. Converts chemical pollution into reusable compounds and reduces dependence on fossil-based fertilizers. Nanosponges and aerogels for oil and chemical spill recovery. How it works. Nanostructured materials like graphene aerogels and cellulose-based nanosponges can absorb oil and organic pollutants up to 900 times their weight. These materials are reusable and can release the captured oil or chemicals for refinement and reuse. By recovering these pollutants, industries can recycle lost chemicals while restoring ecosystems. Impact. Turns catastrophic oil spills and chemical leaks into recoverable, profitable materials. Waste gas utilization via nanostructured reactors. How it works. Industrial smokestacks emit carbon dioxide, nitrogen oxides, and volatile organic compounds. Nanoreactors can turn these gases into valuable chemicals. Nanostructured electrocatalysts convert CO2 into ethylene, a precursor for plastics, using renewable electricity. Nanoporous sorbents capture sulfur or nitrogen oxides and transform them into fertilizers or industrial chemicals. Nano-engineered membrane reactors integrate capture and conversion in one step, making waste to product processing efficient. Impact: transforms factory emissions into raw materials, decarbonizing manufacturing. Nanobiotechnology for waste valorization. How it works: combining nanotech with biology creates ultra-efficient waste-to-resource systems. Nanoparticle-coated enzymes stabilize and enhance enzymes used to digest plastics, breaking them down into monomers for new materials. Nanobioreactors encapsulate microbes that can convert organic waste into methane, ethanol, or biodegradable plastics more efficiently. Nano-encapsulated nutrient recovery extracts nitrogen and phosphorus from wastewater and converts them into agricultural fertilizers. Impact: creates closed nutrient loops and enables industrial-scale recycling of organic waste. Nanotechnology for mining landfills and ocean plastics. How it works: the vast amounts of plastic in oceans and landfills can be mined and reused with nanotech. Nanoparticle-coated magnetic systems capture microplastics from water by binding and pulling them out magnetically. Nanocatalysts for pyrolysis break down mixed plastics into fuels, lubricants, and chemical feedstocks. Graphene and MOF filters separate plastic polymers for reuse in high-value industries. Impact: turns one of the largest environmental threats, plastic pollution, into an industrial resource stream. Smart nanomaterials for zero-waste manufacturing. How it works: nanotechnology enables waste prevention by designing materials that are endlessly reusable. Self-healing nanocoatings extend product life, reducing replacement waste. Smart packaging with nanosensors tracks freshness and facilitates automated recycling sorting. Fully recyclable nanocomposites, strong, lightweight, and engineered for easy disassembly. Impact: moved society from reactive cleanup to a proactive circular economy where waste never accumulates. Nanotechnology in carbon-to-product industries. How it works: atmospheric and industrial CO2 becomes a raw material. Carbon nanotubes, directly synthesized from CO2, turning emissions into strong, lightweight materials for cars, planes, and construction. Nanocarbon materials create advanced electronics, batteries, and even textiles from captured carbon. Impact: reframe CO2 not as a waste product but as a key manufacturing input. Waste as a resource in a nano-enabled world. Nanotechnology provides a vision of the future where pollution and waste are raw materials rather than burdens. From converting carbon emissions into fuels and plastics to recycling e-waste at the atomic level and purifying oceans of microplastics, nanotechnology is enabling a truly circular economy. Instead of extracting new resources, humanity can reuse and upcycle existing materials, reducing ecological destruction while creating economic value. By combining these innovations with renewable energy, AI-driven supply chains, and bio-based production, society can achieve a state where pollution no longer exists, only untapped resources waiting to be recovered and transformed. Nanotechnology is not just a tool for sustainability, it is the foundation of a regenerative future where waste becomes wealth. Nanotechnology provides powerful methods to transform pollution and waste into valuable resources, creating a circular system where materials are continuously reused and emissions are minimized. By manipulating matter at the nanoscale, materials gain unique chemical, physical, and catalytic properties, allowing them to selectively capture, break down, or convert pollutants that were previously difficult or impossible to reuse. This technology addresses multiple types of waste, including gases, plastics, industrial byproducts, organic matter, and electronic waste. Nanocatalysts for waste to fuel and chemical conversion. Nanocatalysts are materials engineered at the atomic or molecular scale that significantly accelerate chemical reactions without being consumed in the process. They are central to converting harmful substances into useful products. For instance, nanocatalysts composed of copper, nickel, or cobalt can convert carbon dioxide, a major greenhouse gas, into methanol, ethanol, or synthetic hydrocarbons using renewable electricity. This process effectively transforms CO2 emissions from industrial sources into usable fuels, creating a circular energy system. Similarly, zeolite and ammonia-based nanocatalysts can break down plastic waste into chemical feedstocks or fuel through controlled pyrolysis reactions. Methane, which is highly potent as a greenhouse gas, can also be converted into methanol or hydrogen using palladium or platinum nanocatalysts, enabling the recovery of energy from landfill and agricultural emissions. Nano-enhanced recycling of electronic and industrial waste. Electronic waste and industrial byproducts often contain rare earth metals, lithium, cobalt, copper, and precious metals such as gold and silver. Traditional recovery methods are energy-intensive and generate additional waste. Nanotechnology provides precise separation and extraction tools. Magnetic nanoparticles coated with selective ligands combine to specific metals in waste streams, allowing for rapid recovery via magnetic separation. Nanofiltration membranes and nanostructured adsorbents, such as metal organic frameworks, MOFs, and graphene oxide sponges, can capture high-purity metals from leachates, enabling a closed-loop recycling system for batteries, electronics, and industrial catalysts. These techniques reduce the need for mining, lower pollution, and recover valuable materials efficiently. Nanophotocatalysis for waste decomposition. Photocatalytic nanomaterials, including titanium dioxide nanoparticles and doped variants, can harness sunlight to degrade complex organic pollutants. These nanoparticles generate reactive species under illumination that break down toxins, pesticides, dyes, and industrial organic residues into basic, reusable chemical building blocks. Advanced nanophotocatalysis can even capture nitrogen compounds from wastewater and convert them into ammonia, a valuable fertilizer, transforming waste into resources for agriculture. Similarly, urban air pollution containing nitrogen oxides and volatile organic compounds can be broken down into benign or reusable molecules using photocatalytic coatings applied to surfaces such as building facades or roads. Nanosponges and aerogels for contaminant recovery. Nanostructured materials like graphene aerogels and cellulose-based nanosponges have extremely high surface areas and porosity, which allow them to absorb and retain large quantities of oil, organic solvents, and other hydrophobic pollutants. These nanomaterials can then release the captured substances for refinement and reuse, effectively turning spills and industrial leaks into recoverable products. Because they are highly reusable, nanosponges minimize the need for disposal and reduce environmental contamination. Gas capture and conversion with nanostructured reactors. Nanostructured reactors utilize nano-engineered catalyst and sorbents to capture and convert waste gases into valuable chemicals. For example, carbon dioxide, nitrogen oxides, and volatile organic compounds emitted from industrial plants can be absorbed by nanoporous materials or captured by electrocatalytic nanostructures and then converted into fuels, plastics, or fertilizers. Nanomaterials allow these reactions to occur at lower temperatures and with higher selectivity, ensuring efficient conversion of pollutants into usable products. Nanobiotechnology for organic waste valorization. Nanotechnology also enhances biotechnological methods for converting organic waste into energy and materials. Nanoparticle-stabilized enzymes can accelerate the breakdown of plastics into monomers suitable for repolymerization. Nano-encapsulated microbes and bioreactors can convert food waste, agricultural residues, or wastewater into biofuels, bioplastics, or fertilizers. Similarly, nutrient recovery from wastewater using nanoscale carriers allows nitrogen and phosphorus to be reused in agriculture, closing critical material loops. Recovery of plastics in landfill mining. Nanotechnology enables extraction of plastic waste from water and soil. Magnetic nanoparticles combine to microplastics in oceans, rivers, or drainage systems and then be removed with magnets, allowing plastics to be collected and recycled. Nanocatalysts can also break down mixed plastics into chemical feedstocks suitable for new polymer production. Nanofiltration membranes can separate and purify polymer streams, ensuring high-quality recycled materials for industry. Smart nanomaterials for zero-waste manufacturing. Nanomaterials can prevent waste before it occurs by creating products that are self-healing, reusable, or fully recyclable. Self-healing nanocoatings extend the lifespan of machinery, vehicles, and infrastructure, reducing the need for replacement. Smart packaging containing nanosensors can monitor product freshness and facilitate automated sorting for recycling. Nanocomposites engineered for disassembly allow materials to be recovered and reused without degradation. Together, these technologies support a zero-waste industrial model. Carbon-to-product nanotechnologies. Nanotechnology also enables the direct conversion of carbon emissions into advanced materials. Carbon nanotubes and other nanocarbons can be synthesized from captured CO2, producing lightweight, strong materials for vehicles, construction, and electronics. This process not only reduces atmospheric CO2 but also generates valuable industrial products, turning a waste gas into a productive resource. Nanotechnology transforms pollution and waste into production by enabling chemical conversion, selective recovery, and energy-efficient reuse at the molecular level. Whether capturing greenhouse gases, breaking down plastics, recycling metals, or converting organic waste into fuels and fertilizers, nanomaterials allow harmful substances to become raw materials for new production cycles. By integrating nanocatalysis, nanophotocatalysis, magnetic nanoparticles, nanofiltration membranes, nanotechnology, and carbon-based nanomaterials, industries can create a fully circular economy in which emissions, industrial byproducts, and discarded materials are converted into valuable, usable products. In this way, nanotechnology does not merely reduce environmental harm, it actively regenerates ecosystems and establishes a sustainable framework for the future.